Seem to be short on cash today. Luckily, as you can tell, I am an alchemist. Alright, maybe you couldn't tell. You probably thought I was some run-of-the-mill wizard. Well, I am not that pedantic. Anyways, I also happen to have no moral quarrels and am willing to break even the most taboo of alchemist laws to transmute gold. It's technically not transmuting gold.
And who are you?
The alchemist of the modern age.
What?
I'm a chemist. Chemistry. Molecules. No. Elements. Whatever. You have obviously come to witness my magic. I'm going to turn these dull, colorless, mysterious liquids into gold. You're actually just reacting lead nitrate and sodium iodide to create lead iodide, which creates kind of like this goldy substance. But I'm going to turn these invaluable liquids into gold. I will prove it to you. Ta-da! Gold! It's just not real gold. That's all I'm trying to say. So, how did this so-called alchemist create a little glass of gold? Well, sleight of hand and video editing. And, well, chemistry, of course.
Hello and welcome to Greg's Lab. Today we're officially going to debunk that pesky alchemist by proving that what was created was not gold, but in actuality, lead iodide, and, well, talk about the chemistry behind it. Our fiend of a friend back there, as I tried to explain before, reacted aqueous lead nitrate with aqueous sodium iodide to produce a yellow precipitate of lead iodide. Let's make some gold. To perform this reaction, you'll need a few things. You'll need 50 milliliters of 0.2 molar sodium iodide, which to create based off of our solid solution, you'll need about 1.5 grams mixed with 50 milliliters of water. You'll also need 50 milliliters of 0.20 molarity lead nitrate, which to create the solution will require 3.3 grams of solid lead nitrate. You'll also need a 50 milliliter graduated cylinder, a 100 milliliter beaker for initial prep, a 1 liter beaker, a Florence flask, a burner, a funnel, and some filter paper for the actual reaction. Just a note of caution, all the chemicals we'll be working with today can be hazardous if ingested or inhaled and will cause irritations if contact is made with the skin. Be sure to wear your splash goggles, closed-toed shoes, and an apron. Now that we have the proper concentration, we can take the next step in making our gold. We're going to mix the lead nitrate and the sodium iodide solutions into the 100 milliliter beaker. You'll notice how a yellow precipitate is forming. This is lead iodide. And yes, this will be the gold. Bear with me here. Next, using the filter paper over the 1 liter beaker, we're going to capture the solid lead iodide. Set that aside and add distilled water over the supernated liquid from the previous reaction until there's approximately 300 milliliters. Then, place over heat on the burner. Once boiling, we're going to add the solid lead iodide precipitate until the solution at 100 degrees Celsius is saturated, which is evident by the precipitate no longer dissolving. While still hot, pour the saturated solution into a 500 milliliter Florence flask and allow to cool naturally. This is where the magic happens. You'll notice as it cools, the lead iodide will once more precipitate out, but this time into what looks like little gold flakes. Once fully cooled, place the stopper in the flask and voila, you have your gold. But while we wait for the lead iodide to precipitate out, let's talk about why it looks like this. Lead iodide has the Pearson notation of Hp3. The lowercase h means it's part of the hexagonal crystal family, and this is not noted, but lead iodide specifically has a rhombohedral lattice system. The P stands for primitive centering, which simply means the only lattice points are on the corners of the shape. Finally, the 3 represents the numbers of atoms in each unit cell. Normally, when prepared with cold solutions, the gold platelets are small and can be described as giving the solution a silky effect. The reason we will have these larger crystals is because the lead iodide solubility increases differently with temperature, and we place the solution over heat. Lead iodide's KSP, or solubility constant, is 4.41 times 10 to the negative 9 at 20 degrees Celsius, so fairly insoluble. But, because solubility constants are functions of temperature, we can change the temperature factor to increase solubility so we can selectively recrystallize the lead iodide into larger crystals that we would have initially created. As we return, we notice that it's precipitating as large golden crystallized flakes.